Okay, now we have an infinite cylinder of wire carrying a total current I. My cylinder has radius R. So this cylinder goes on and on forever, and it's in this picture here, the current is flowing in this direction. I want to find the magnitude of the magnetic field both inside the wire at some distance r from the center, from the axis of the cylinder, and outside the wire, that'll be part B down here, where I'm some distance r, where little r is bigger than the radius. We did a similar problem. We were doing Gauss's law for charge. So we're going to create an Amperian loop. First we're doing r, little r is less than big R. So I'm going to create an Amperian loop that exploits the symmetry of our physical situation. So that's going to be a circle because we have cylindrical symmetry here. So we know just by symmetry that B, the magnetic field, follows the right-hand rule. B has to go in circles. So the magnetic field lines would go in circles and has to be constant a distance r away from the center. B in magnitude here should be the same as here and here and here and here and so forth. So I'm going to exploit that symmetry. So I'm looking at it from the wire's point of view. The current now is coming straight at our eyeballs. Here's the entire cylindrical wire. I've built an Amperian loop someplace in the middle, some distance r away from the center. I know B is constant along that Amperian loop, and I get to choose my direction here, which way I want to go around that loop. I'm going to choose to go around counterclockwise in the same direction B does, because I want B and DL to be parallel or perpendicular. In this case, B and DL are parallel. Everywhere, right here, I would have a B vector that points like that. DL would also point like that because I'm going around the loop in that direction, counterclockwise. So Ampere's law says and again, this should be a loop integral. To be really formal, I should draw that little circle with the arrow there. The line integral of B dot dl is mu naught I enclosed. This is Ampere's law. I need to find out how much of my current, my total current I, passes through this circle here. So I'm going to have to use some kind of current density here. So I enclosed will be my current density times my area enclosed. In this case, J, the current density, will be current per cross-sectional area because my cross-section is an area. So this is the trickiest part right here, is figuring out I enclosed. What fraction of my total current passes through here? If little r equaled big R, it would be 100%. It would be all of I. If I went halfway out, if little r were half of big R, I would not capture half of the current. I would only capture a fourth of the current. And we'll see why in a minute. So my current density is the total current divided by the total cross-sectional area. This is amps per square meter. So that's all of I divided by pi r squared, because that's my total area. Then the I enclosed is that J times my actual area enclosed. Because I'm not, all of I is here, I'm only capturing this much of I. So take that J times the area enclosed. Area enclosed is pi little r squared. The pi's cancel, and I get this fraction, I times little r squared over big R squared. If little r equals big R, that would just be all of I. And again, I said this earlier, if little r equals half of big R, then I would get a 1/2 squared there. I get a quarter of the total current. Okay, that's the trickiest part of the whole problem, is finding I enclosed. So the left side, B dot dl, because B and dl are parallel, and because B is constant along that circle, I can factor out the B. The integral of dl is literally just the length of the curve, 2 pi little r, and that's supposed to equal mu naught times that I enclosed, that right there. One of the little r's cancel. Divide by the 2 pi, we get this. That should remind you a lot of the Gauss's law problem we did with charge, but then we had a Gaussian surface and we had a volume enclosed. Now we have an Amperian loop and we only have an area enclosed. We're one dimension smaller in both of those. Okay, now we're going outside the cylinder. So I want to find the magnetic field out here. Excuse me, a distance little r from the center, where little r is bigger than big R. So looking at this from the top, so the current's flowing out towards our eyeballs right now. All the current lives in here. I'm way out here. I know by symmetry, B should be constant around this circle and should be tangential to the circle. So my Amperian loop looks like this. This is my loop, and I'm traversing this in a counterclockwise direction so that dl points counterclockwise at every point. It's tangential to the surface. So I've drawn these at separate spots because it's hard to drill them at the same spot. But at this spot right here, B and dl would both point this way. B and dl are parallel. That's the whole point. If B and dl were not parallel or perpendicular, you can't do the line integral. Because they're parallel, the line integral around, again, this should be a loop curve, around that loop will be magnitude of BL times the length of the curve. That's what integral of DL is. The total length, 2 pi r, times magnitude of B. I enclosed. What fraction of my total current passes through the cross-sectional area here? Well, I could play the same game I did before. The same J, we have the same current density. My area enclosed now, the area that actually contains current, is this area. That's why I did this little shading here. Those cancel, we just get I. All the current flows through here. I've got all this space out here with no current. What fraction of the current did I catch? All of it. I enclosed is I. So 2 pi RB equals mu naught I. Solve for B, we get this. And again, this is just the magnitude of B. We should also write here, B goes in loops counterclockwise if the current is flowing towards your eyeball.